Long after university, I stumbled upon Numberphile. You may not believe it, but it is this channel and not any number of chemistry ones that is tops in my bookmarks. Through Numberphile and others, my enjoyment of and appreciation for mathematics has only grown. But the origin of this particular video, and possibly a series, all begins in the 1960s with Neil Sloane's graduate school project. This project involved cataloging sequences, like the two on the screen now. If you can decipher those descriptors to tell me what they actually mean, that'd be great. In the early 1970s, with over 2,000 entries, Sloane published the Handbook of Integer Sequences. The collection of sequences did not stop with the publication of the handbook, and by the mid-1990s his list had doubled. New sequences and a bit of reorganization put these two easy-to-understand ones at the beginning of the Encyclopedia of Integer Sequences. Luckily for Sloane, the internet as we would recognize it was becoming a household feature. Soon, the Online Encyclopedia of Integer Sequences, or simply OEIS, was born. I was first introduced to it in the video titled Sloane's Gap, and while Sloane himself does not feature, he has done so in numerous videos since with his love of sequences on display for all to see. I started to wonder if I had what it takes to find a worthy sequence. After all, the OEIS contains roughly 392,000 entries as of January 7, 2026, so how difficult can it be to find one more? Luckily, the OEIS is kind enough to provide a suggested pre-submit checklist. And of those 11 suggestions, I have exactly 0 of them, so I should get to work. Before I start, I'm well aware that finding something previously unknown or at least useful for mathematicians is highly unlikely, but that's not the point. If I learned something new, either about mathematics, coding, or something else, then it was worth it. My journey will involve the search for perfection in number form. A so-called perfect number is one where the sum of all the proper divisors, or aliquot sum, is equal to the number itself. This can be restated as the sum of all the divisors is equal to twice the number. For example, 6 is a perfect number. With proper factors of 1, 2, and 3, it fits the definitions as 1 plus 2 plus 3 equals 6, but if we consider all the divisors, this includes 6, and 1 plus 2 plus 3 plus 6 equals 12, which is 6 times 2. Here are the first few, and the entire sequence is found on the OEIS titled A000396. Mathematicians do not know if there is an infinite number of them or not. Interestingly, they are linked to Mersenne primes, which are primes of the form 2 to the p minus 1, where p is prime. Like perfect numbers, mathematicians do not know if there are an infinite number of them, but the search is going strong. If you want to join in the hunt, head to mersenne.org for more information, and even the chance to earn $50,000 by finding the first Mersenne prime with more than 100 million digits. It won't be easy though, because the search isn't even close. In October 2024, the most recent and largest Mersenne prime was found. The simplest way to write it is 2 to the 136,279,841 minus 1. This is the first Mersenne prime to have a prime power in the hundreds of millions, and the number itself is over 41 million digits long. I'm not sure how large the numbers are which are currently being checked for primality, but as of recording, all exponents below 139,011,709 have been checked at least once. It is known that for Mersenne primes, there exists a perfect number of the form 2 to the p minus 1 times 2 to the p minus 1. You might believe this is the result of a modern proof, but it actually goes back over 2,000 years to Euclid, which is amazing. When this most recent prime was discovered in 2024, this means a new, largest perfect number with just over 82 million digits was found. If mathematicians prove infinitely many Mersenne primes exist, they will prove infinitely many perfect numbers at the same time. But numbers aren't limited to twice the sum of all the factors. These are multi-perfect numbers and are known to exist for all multiples from 3 up to and including 11. The following sequence contains the first 6 tri-perfect numbers. And that's it. While 4 perfect and larger multiples are either confirmed or thought to have longer sequences, it is believed all of them are finite. This is one of the things I love about math. Similar properties, and in one case there is likely an infinite sequence, and all other cases finite. What is also interesting about all versions of perfect numbers is that none of them are odd. Despite never finding one, mathematicians have not proved that odd perfect numbers definitely do not exist, so I'm going to start here. I'm under no illusions that I will find the elusive odd perfect number. Instead, my goal is to find something that isn't on the Wikipedia page for them. Something I can understand, that is. Now it's time to put my coding skills to the test and start factoring some numbers. While it works, this wasn't a serious attempt at factoring numbers because it's hilariously inefficient. Factoring numbers efficiently is a fascinating topic, and I'm sure YouTube is filled with plenty of videos explaining it from a mathematics and programming perspective. Needless to say, the code I will use is way better than the nonsense on the screen now. For the record, I did run this code on my laptop for fun, and it took about 12 minutes to factor the first 100,000 numbers. Perfection is all about the sum of the factors, and since I know I won't find any odd perfects, I will go for ones that are pretty close. These are any numbers whose aliquot sum, or sum of proper factors, is within 10 of the original. 10 is a completely arbitrary choice, so I can adjust to other values as I want, and there isn't anything of the sort on the Wikipedia page. I will set my improved code to search up to 1 billion. And after a 10-minute search, here's what it found. We see some close results early on, but that doesn't seem surprising given the numbers themselves are fairly close to that difference range of 10 I'm searching within. To me, the interesting results don't start until we get to 315, and it's a lovely coincidence. Including 315, there are 6 consecutive results, all of which end with a 5, where the absolute distance to perfection is 6. Perhaps there is an obvious reason for this to be as good as it gets, but I have no idea why. Should any number theorist happen upon this video, an explanation would be greatly appreciated. I did search beyond 1 billion and got no additional hits. What I have found about odd perfects isn't on the Wikipedia page, so I fulfilled one of my requirements. But is this list of numbers OEIS worthy? There's only one way to find out. So someone not only had the same idea, but they had it more than 20 years ago, and they've searched nearly 11 orders of magnitude beyond what I did. Oh well, I did my best, but 10 was arbitrary, so what about 100? Maybe something worthy lurks in this expanded range. I changed the range to 100 and the search space up to 100 billion. It took my laptop 4 days to complete the search, and here is what I found. We see lots of results that aren't too far off from the range we were looking at, but once again the tendency is for the differences to be a multiple of 6. This includes 5 numbers beyond what I found initially, one of which is nearly 50 times larger. But there are a few interesting values worth pointing out. As you can see, it is still the case for most numbers end with a 5. The largest number found that ends with a 7 is only 147, and with a 3, 273. As for 1, the largest is 351,351, and 9 has the largest such result at 20,487,159. Those numbers are neat, but for me the most interesting are 78,975 and 1,805,475. With differences of 26 and minus 70 respectively, they are the largest ones I've found that are the closest to perfect, not within a multiple of 6. Unfortunately, some of these new values, even the largest ones, appear in the OEIS under sequences somewhat related to what I've been searching, so it seems I have nothing to submit and a lot of number theory to learn. It has not all been for naught, however, because technically I did find a sequence worthy of the OEIS. I just wasn't first. I know being technically correct is the best kind of correct, so I'll finish this video concluding that technically worthy is the best kind of worthy. And until I am ready to present my next technically worthy sequence, thank you very much for watching.